Dear students, let's resume back our discussion on advanced digital signal processing video lectures. In this video lecture, we will continue our discussion on implication of downsampling and upsampling in frequency domain. I am sharing the screen. In the previous video lecture, we have discussed about the implication or the effect of downsampling of a sample signal in frequency domain. So this is just a very quick recap. So we have seen at the beginning time domain relationships for both downsampling a discrete sequence and upsampling or expanding a discrete sequence, right? And downsampling is looked at taking out alternate m samples with m-1 samples gap to collect the x of mn from x of n. Okay, that is downsample. Whereas expansion is looked at introducing m-1 zeros in between the samples of x of n, or l-1 zeros in between the samples of x of n, right? And we have written a closed form expression. This we will base now, and we will discuss further on what is its effect on the spectrum of the expanded signal, and also do we need to do any more filtering operations to resume back the original sequence x of n or the original signal xc of t, right? So this is all we discussed in the previous class. We have discussed about when we explicitly have a downsampling, what's the effect in frequency domain. Please note a small correction here. So there is 1 by t term, okay, a constant term that is missing in the previous discussions. Please note and add that. So the discussion is done in like without a scaling, taking care of the scaling term or the 1 by t term. So you please note in every expression that's what was missing. So in case when we downsample by m times, the effective time period here, that is t dash, is equal to, so here t dash is equal to mt, okay, and hence the term that multiplies before is 1 by mt, okay, or 1 by t dash, right? This I request you to note. This is the same in all of these expressions. That was missing earlier. Okay, since it is only a constant term, the spectrum, all the discussion is exactly same. But note that when we are sketching the spectrums, this constant term also play a role in terms of its magnitude of the spectrum, right? Height of the spectrum. That we didn't pay more attention because we were conceptually understanding the spectrum and its implication of downsampling in frequency domain. So that was the main discussion in the previous video lectures. So and hence this constant now can be easily taken care along with the previous discussion that we had. So till here now we can write 1 by t term here, which is absorbed in this, okay, whereas 1 by m term here, okay, from 1 by mt, right? This term still be there in the downsampled spectrum. So there is a difference between downsampled spectrum and the original spectrum by this constant term 1 by m in scaling as well, right? Please note that. Okay, so here if we explicitly would like to put, so here it is 1 by t, and once comes here it is also the xd, right? So here 1 by mt. Okay, this is the height of this peak. Okay, so we didn't pay much attention there because we were conceptually understanding the spectrums and the like implications in frequency domain and so on. But however, for accurately representing the magnitude as well, this term is also important, right? So this is 1 by t and this is 1 by mt. Okay, that's the height of the, right? Okay, so 1 by t everywhere, and this is 1 by mt. So this is only filtered. So here still it is 1 by t. Right. So now let's move on to the discussion on what happens when we do upsampling. Okay, so let us write, let x of n be the sequence given to us, obtained from xc of t. Okay, by sampling with time period, okay, capital T, that is with a delta train, right? So s of t is obtained by xc of t into delta of t minus nt, where n equal to minus infinity to infinity. Okay, so from this x's of t, we have x of n by normalizing with the time period capital T. And it may have some spectrum. We will sketch roughly its spectrum, right? And now the expanded signal x e of n is obtained from x of n. How is it obtained? So x of n by L for n being integer multiples of L, right? And 0 else, by expanding it with zeros in between L minus 1 samples and taking the samples of each, say from the original signal, and putting them L units apart, we have x e of n. And this can be compactly written by the expression x of k delta of k minus nl, or n minus kl, n minus kl. Okay, it is n minus kl, k equal to minus infinity to infinity. Okay, so this expression consolidates the two different conditions in a single form, right? As you can see, when n is multiple of L, you sample from the original signal. Otherwise, you just place the zeros there in x e of n, right? And now we would like to first mathematically see how the x e of e power j omega looks like, or the discrete time Fourier transform of the expanded signal, right? So let us apply this directly here. Unlike in the previous downsampling case, here we can directly use x e of n and it's substitute in the expression and get the answer for expressing x e of n, x e of e power j omega in terms of x of e power j omega, right? What is the expression? X e of n e power j omega n, right? And let us now substitute n varying from minus infinity to infinity. When we substitute it, summation n equal to minus infinity to infinity, x e of n is, okay, let us substitute here, is equal to n is equal to minus infinity to infinity x summation. Okay, let us bring in another. X of k delta of n minus kl into k equal to minus infinity to infinity again. Okay, and then this is e power j omega n, right? So now let us see which terms we can group first. See, these two terms only are dependent upon n, right? And this term, so we can bring sigma k out and then use n terms one place. Let's do that. Infinity, infinity. K equal to minus infinity to infinity. Okay, x of k, and let write these terms. N equal to minus infinity to infinity. See delta of n minus kl e power j omega n. Okay, so what do you think is this? This is a delta function and n varying from minus infinity to infinity. So this delta function for any given k, okay. So if you want to bring for a fixed k, this is non-zero only when n equal to kl, and hence this can be written compactly as what? This can be written as sigma k equal to minus infinity to infinity first term into xk into what is this? This n takes the value kl when it is non-zero, when delta function is non-zero. For rest of the values in this summation, okay, the delta function is 0. And hence we can directly write here j omega k into L, right? So now in essence or in summary, so this is inside, this is same as this. Okay, so you can see the relation between them. Okay, so these two are same, right? Okay, so now we can see, we can write the final overall expression as, okay, overall expression as x of, sorry, x of e power j omega, x e of e power j omega is equal to summation k is equal to minus infinity to infinity xk into e power minus is there everywhere. Yeah, so minus is missing here, so you can keep a minus. Right. Okay. So now e power minus j omega into k into L. Right. So now how do we write this in a compact form or explicitly in terms of x of e power j omega? So we want to write this as x of e power what? J instead of omega, we can write this as omega into L. Right. And this is equal to x e of e power j omega. Right. So if you can just reorganize this, if you reorganize this is equal to summation xk e power minus j omega L into k. Right. This now frequency is being increased by L times or omega L. So omega axis is being compressed by L times. When we sketch it, the omega axis will get compressed by L times. However, the sampling frequency gets increased by L times. Okay, when we do expansion, right? So what, say when we are doing XFN, its sampling period is capital T. So F as sampling frequency here is 1 by capital T, right? Whereas when we do expansion, what's happening? We are keeping for every L, like the number of samples per second increases, and hence the sampling frequency is L by T, right? It increases by L times. Okay. Right. So, however, when we sketch it, so assume that if I have a spectrum, let us start with x of e power j omega directly, because we were familiar. Now, for the example we have taken, x of e power j omega will sketch, right? So assume that we have a triangular x of t. So just for completeness, if you would like to bring in the discussion of the same example, so we have actually, we are given that this is minus 500 to 500 and this is xc of j omega. Okay, and assume that we have done all this omega axis, right? And we have sampled it with initial sampling period of 1 by 2000. Okay, RFS is equal to 2000. Okay, and sketch the spectrum, that is x of e power j omega. Assume that we have obtained x of e power j omega. Okay, with this fs we have got it, right? Let us sketch x of e power j omega. Minus pi by 2 to pi by 2. Okay, it comes minus pi by 2 to pi by 2, and again it repeats at, this is pi and this is 2 pi. Sorry, it repeats at 2 pi. Correct? And this is pi, and this is 3 pi by 2. Okay, and similarly this side, this is minus pi, right? And then this is minus 3 pi by 2, and this is minus 2 pi, and hence this repeats, this spectrum repeats at minus 3 pi by 2, minus 2 pi, right? And this is x of e power j omega. Okay, this you can see from the earlier discussions, and 1 by t is its height. Okay, so now what is the effect of upsampling here? Okay, so what is the effect of upsampling? Now, if we assume that if I want to sketch expanded spectrum, okay, so what will happen to the omega axis? This is omega axis here. Okay, what will happen to the omega axis now? It will, see, in time domain, the number of samples has increased. Okay, L times per cycle, right? That's why there is an expansion in time domain. Since there is an expansion in time domain, usually because of the inverse relationship between the representations of time and frequencies, you can see that there is the compression happens in the frequency domain. And omega L means that this is omega dash axis. Okay, so what will happen? This is equal to omega into L. See, let the upsampling factor be 2, right? So let L be equal to 2, L equal to 2 times. So what we are doing? We are doing, say, upsampling by 2 times. Assume that I would like to do upsampling by 2 times, right? And then sketch the spectrum there to obtain xe of n, right? And you have x of n to xe of n. Okay, so this we would like to sketch. What will happen? There is a compression by, say, omega L means here. So you can see that the spectrum gets reduced by, like, compressed by half. So we will sketch it here. This is 0. And hence now, see, this is okay. And as you can see, x of pi by 2 now, say capital X of pi by 2 now appears at pi by 4 in this spectrum of omega dash, right? Pi by 4 to pi by 4. Okay, as you can see from this expression. Okay, so you can see that capital X of e power j pi by 2 now appears at, okay, pi by 4 here. So pi by 4, if you put for omega, then pi by 4 into 2, that becomes pi by 2. The value at pi by 2 now comes and sits at pi by 4, right? So that you can see from this relation. Okay, so right. So now let us complete the sketch of the spectrum. And again at 2 pi, we have actually another spectrum. And in between, what does it happen? See, this 2 pi now moves to pi because the whole like spectrum is compressing. So because see 2 pi here, if you want to, whatever is the value that is at 2 pi now, okay, where will, if this has to be 2 pi, then here it is enough to put pi. Omega equal to pi is equal to pi into 2, that is 2 pi. Okay, so there is a spectrum here. So let us sketch with different colors to have a better clarity on the spectrum. So I will be superimposing with other color here to have a better clarity. Okay, so now where does this blue spectrum will come? That is exactly at pi, right? So let us put it at pi, sketch it at pi, right? And there may be another spectrum there that comes and sits. Okay, that comes and sits at this location. So let me sketch this also with the same color so that actually you can easily relate. So this is with, okay, this is same as that spectrum, right? Right. And here whatever you get is a third thing that is at 2 pi. This is not shown here, but it may be at 4 pi in omega, sorry, in 3 pi. Sorry, it's in 4 pi in omega axis, right? Here 2 pi is equal to 4 pi in the x of e power omega, right? Okay. So similarly, where does this appear? So let us sketch this with also different color to have a better clarity. Right. So now where does this appear? At minus pi, right? So at minus pi, you can see that there is a spectrum. Okay, this compresses and appears at minus pi. This one compresses and appears at minus pi. Okay, similarly the other ones. Okay, so I'm not sketching, but there will be another spectrums. Okay, so on, so on. Right, and this is pi, 3 pi by 4 and 5 pi by 4. Okay, similarly minus 3 pi by 4 and minus 5 pi by 4. Okay, similar, yeah. So this is how the spectrums are. And what is the height of the spectrum? Is still 1 by t, because there is only compression factor here. In the expression there is no 1 by t or change in frequency, change in amplitude terms, right? So because of the expansion in time domain, what is the implication in frequency domain? The spectrum compresses in the frequency domain. And you can see that if you see the gross range of minus pi to pi in frequency domain, say for example here to here, okay, this is the range we have to see because it is periodic with 2 pi, right? In this range, you can see that there are some additional spectrums, okay, because of the repetitions of x of e power omega 2 pi and minus 2 pi, you have additional frequency components introduced in xe of e power omega, right? Here also minus pi to pi indicates this region of the spectrum that repeats, from minus infinity to infinity. And hence, now we should see, if you want to get back from xe of n, the expanded signal, okay? But with the spectrum being compressed, okay, but the spectrum being yeah, corresponds to the upsampled signal, but with the signal without getting the additional frequencies introduced. Okay, what operation should we do is referred to as interpolation, right? So we should do some operation to get interpolated signal xi of n, right? So what is this interpolation needed for? This interpolation is needed for what? This interpolation is needed for extracting Okay, extracting only this component of the spectrum, okay, and from in the range minus pi to pi, and not being affected or not being introduced with additional frequency components because of the repetitions in x of e power j omega. Okay, we would like, ideally, we would like to avoid, okay, we would like to avoid this term, okay, and this term, okay, in the minus pi to pi range. Same thing happens everywhere because the spectrum is periodic with period 2 pi. Any of the discrete time Fourier transform spectrum is periodic with period 2 pi. So to do that, we can use a low pass filter, right? And what should be the cutoff frequency of this low pass filter? That is the next question, right? So what should be the cutoff frequency of this low pass filter? The cutoff frequency of this low pass filter should be such that, see, usually how did we design a low pass filter in terms of say to avoid anti-aliasing? We have seen that the low pass filter captures the range minus pi to pi, okay, in the in the x in the expanded spectrum. Okay, so now the spectrum with this is itself is the expanded spectrum when compared to the, okay, the upsampled spectrum. So the spectrum should capture the range minus pi to pi in the x of e power j omega, and that should be the criteria for selecting the cutoff frequency of low pass filter. And thus, what will be that in the, say, x e of e power j omega? This is x e of e power j omega. Since we need to apply filter on the x e of e power j omega, what is the range that captures minus pi to pi in x of n? Okay, or x of e power j omega. That's what we need to see. What is the range it captures? Since we are upsampling by L times, okay, this range is from minus pi by L to pi by L. Because the compression of the axis happens by L times, you should capture minus pi by 2 L by 2 pi by L for capturing minus pi by to minus pi to plus pi range in the original spectrum x of e power j omega. Fine. So for that reason, there should be a low pass filter here. Okay. And that should have a cutoff frequencies minus pi by L to pi by L. Okay. And this will give us a interpolated discrete signal. Because this is an interpolated discrete signal because it has the spectrum exactly having same frequencies as that of x of n. However, it has a like the compressed frequency axis, or it has a it has more samples in the frequency domain, right? So that means, say, if I consider minus pi to pi range, see the sampling frequency I can consider to, say, the number of samples I can consider with respect to this, we can assume that it is roughly double the number of samples, okay, that corresponds to this spectrum than this spectrum, right? Now let us see what mathematically how to bring in this filter and get this xi of n. Okay, right. So x I of n, how do we get? We get after filtering. So let us look at the process. So you have x of n, and then you upsample by L times. Once you upsample, the spectrum gets compressed, and they, in addition to the the spectrum at minus pi to pi range, you may have the spectral components that comes from around 2 pi and minus 2 pi also to appear in minus pi to pi range in the expanded signal or compressed spectrum, right? To avoid that, we apply a low pass filter of cutoff frequency minus pi by L to pi by L. This minus pi by L to pi by L comes because you need to capture minus pi to pi in x of e power j omega, right? and there is a compression of L factor in the frequency domain in omega dash or the expanded signal. And hence, you should have a low pass filter here. Okay, you should apply low pass filter to have only those frequency components that are there in the original signal, and remove the rest of the frequency components that comes because of upsampling or expansion, right? And this is a compressed spectrum, but it has the spectral content exactly similar to the original spectrum. Okay, x of e power j omega, x of n, right? And this will give us x e of x interpolated of n, right? And this is intermediate result is x e of n. Okay, in frequency domain, through this process, what you get is a pure spectrum that it appears exactly like the original spectrum, but compressed by half. Okay, right, and then compressed by L times. Okay, now let us bring in mathematical relationships. So first, let us get this h of n. How will be this low pass filter, right? So upsampling filter. HL of n is this, right? So ideally, we wish to have HL of 0 to be 1. Okay, so that actually in time domain, the sample like that we get will be exactly similar to x of n, interpolated sample. And hence, we introduce a factor uh, L here. Okay, so that this factor L is introduced everywhere, and hence the height also, this comes as a height in HL of j omega. So we would like to take, rather than height 1, we would like to have a height of L in frequency domain spectrum, and hence in time domain, the sample at HL of 0 will be 1. HL of 0. Now if you consider, it is sine pi L by pi n by L, n tends to 0 is equal to 1, right? This is what we ideally desire, because see, if we now try to find xi of n, how do I write in terms of xe of n and the low pass filter? So we write here xi of n is equal to convolution of, this is multiplication in frequency domain, right? So you are doing multiplication here in time domain, it is xe of n convolution with hl of n, right? And this, see, this convolution should not introduce any additional artifacts or the additional scaling effects to the original signal x of n or xe of n. That is the reason why we wish to have xl of 0 to be 1. Okay, and to ensure that, we should have a frequency domain spectrum having height L. Okay, so thus you should note that the height of this is L. Let us bring in the same color. Height of this is L. Okay, right. So let us complete this expression. So now, given this can be written as convolution, say k equal to minus infinity to infinity x e of k. Okay, so let us expand what is x e of k. Okay, so what is x e of k? Summation. Okay, you can write okay, let this be n, so that we can this is n equal to minus infinity to infinity x of n L of k minus nl. Okay, so let us write fresh. Okay, let us expand this in the next slide. So you can see now xi of n is obtained by convolution of xe of n and the low pass filter. Okay, and xl of n through expression is what is this? Okay, so this we will use in the next slide, to next page, to write what is xi of n explicitly. Okay, right. And please note that this HL of n can also be written as sine pi by ln by pi by ln. So it's a pure discrete sinc function. Okay, fine. So now let us write explicitly what is xi of n. Okay, is equal to summation x go k xe of k into what hl low pass filter of n minus k. Okay, this is by expansion, and hence this is equal to summation k xe of k into what is this h. So rather than expanding this, there is a even simple procedure to do this. So what we do is we just expand here. We write xi of n is equal to xe of n convolution with hl of n, right? So let us only expand xe of n. So if we expand xe of n, what is this? K equal to minus infinity infinity x of k del of n minus kl, right? This is what is x e of n in terms of x of n or x of k convolution with hl of n, right? And hence, see, you know that convolution with any delta function or delta function with any function is the same function shifted by the argument of the delta function, and hence you can write this as minus infinity infinity x of k del hl of what n minus kl. That's all. Okay, so this convolution, right, is this. Okay, because convolution with delta function is same function and the argument is replaced by argument of the delta function. Okay, the function appears at that delta locations. In other words, okay, the sample or signal reappears at delta location or shifted by delta location. Okay, right. And this now you can also write explicitly xi of n is equal to summation. What's the operation happening here? No, it is essentially same as similar to as reconstruction, okay, but with discrete sinc, and hence the reconstruction or the interpolation happens in between the samples which are non-zero, or the zero samples are being reconstructed through this process. Okay, this is what is the interpolated signal or sequence. Okay, so and in frequency domain, what does it happen? It simply the spectrum is same spectrum. I will sketch the spectrum of the xi of n here just for completeness. Okay, so only from minus pi to pi range. Okay, this is 0. So the spectrum is simply there between. Let us bring in the same color. Right, minus pi by 4 to pi by 4. That's all. And the spectrum have height, says it is obtained through low pass filter with a filter of gain L. Okay, and hence this is L by T. Okay, the height is L by T, and this is xi of e power j omega, right? Because this is a discrete spectrum, it repeats for every 2 pi. Okay, so I have sketched only from minus pi to pi. That's it. Okay, this is the frequency spectrum of this. Okay, this is for it also. Okay, fine. You can see that this looks like original spectrum. Okay, if you see in minus pi to pi range, it looks like original spectrum, but with a compression, or the say if you see with respect to this sampling rate, if you consider, okay, you have now roughly you can have double the sampling rate fs. Oh, still avoiding the aliasing, right? You can afford to sample this original signal if you know that you will be doing upsampling by 2 times. You can afford to sample this, okay, by double the half the sampling rate, right? So that is than what you have seen here. Okay. In essence, it is good enough to sample at Nyquist rate, okay, to avoid any aliasing in the upsampled signal or by any factor of upsampling, right? Thank you. So in the next video lecture, we will look at how to have a, if you want to perform sampling rate conversion that is involving both upsampling and downsampling, or changing the sampling rate, not by an integer factor. How to do it? Here we are increasing the sampling rate, means we are increasing it by integer rates. Also, when we are downsampling, we are decreasing the sampling rate by integer factor. So if I want to increase the sampling rate by 1.5 times, then we want to increase the convert the sampling rate by a fractional factor. And how do we do that? That we will see in the next video lecture. Thank you.